Hello, my name is Tsoof. I'm from the Faculty of Aerospace Engineering in the Technion, Israel. This presentation is about dynamic shape sensing of the A3TB wind tunnel model using fiber optic strain data and the Kalman state estimator. As new aircraft configurations are trending through increasingly more flexible wings, aeroelastic phenomena become more prominent, posing challenges on aircraft design. Among them is flutter instability that often leads to catastrophic structural failure, thus limiting an aircraft's flight envelope. On the other hand, wing flexibility can be beneficial and leveraged to achieve optimal performance. The benefits and challenges of flexible wings motivated several research programs aimed at flexible wing control for flutter suppressions, load elevations, or performance optimization. For that, information on the wing deformation is needed during flight. Our study, which was presented at SciTech 2022, proposed strain-to-displacement method that blends in strain data and an aeroelastic plant model. The method was demonstrated with the wind tunnel model shown in the picture. A Kalman state estimator was used adaptively weights measurement and simulation data to estimate strain and displacements at non-measured locations, clears out noise influence, and overcomes measurements error. The current study applying the shape sensing method on the A3TB wind tunnel model shown in the picture. This model is a full scale of the A3TB platform and aeroelastic demonstrator. See the paper for full details. Additional objectives are studying the impact of using different strain model sets or different aeroelastic models. This test was conducted at the Michigan University, involving research groups from Michigan University, Ohio State University, and the Technion Israeli Institute of Technology. For those who are not familiar with the initial study, here's a brief explanation. The deformed shape of the wing can be obtained from strain data. When good strain measurements are available, the model displacements, marked here as Xi, can be evaluated using the least square process while using strain modes, marked here as Psi. Both strain and displacement modes can be computed from finite element model or ground vibration testing. Fiber optic strain sensor has seen in the recent years widespread use in aerospace. The advantages are high sample rate, high accuracy, and easy to install, therefore a good fit for shape sensing. However, all measurements are subject to noise, which spoils the results. Plus, the system can experience process noise, such as turbulence or weight reduction. Flexible wings, the dynamic model is based on the aeroelastic plant state space. The state vector includes the model displacements and velocities, aerodynamic lag terms, and the control surface deflections and their time derivatives. The state and input matrices A and B can be computed for nominal airspeed by using aeroelastic software like Zero. The output matrix C is defined by the strain modes at the sensing points, Psi-S. We'll see next whether and how different modes set at matrix C affect the estimation. This model assumes random process and measurement noises W and V with the covariance Q and R. The Kalman state estimator used the state space equation as a predictor based on previous data points. Then, correct the former based on the measurements while multiplying the innovation by the Kalman gain matrix K, which based on the noise covariance matrices. The Kalman gain can be modified to rely more on the measurements over the model and vice versa by changing the values of the noise covariance. In the extreme case of fully relying on the measurements, the solution will converge to least squares. While the Kalman gain goes to zero, the state estimator is fully relying on the model. The process noise can be estimated from simulation or a test in controlled environment. In the current study, the process noise was observed from zero input responses in the wind tunnel. The measurement noise was studied from static loading. Now, let's move on to the test case and the results highlights. The A3TB model is 3D printed from nylon 12 material has a NACA 0012 airfoil, 295 mm chord, and 1352 mm span. It has 4 trailing edge flaps which used in the wind tunnel for excitations. Strain at more than 300 points on the spars were measured with a single fiber optic, and the reference wing shape was measured with motion recovery system. The wing was tested in the wind tunnel at airspeed of 24 meters per second with 1 to 10 Hz frequency sweep input at control surfaces 3 and 4. Here are the first strain mode sets used in this study, computed with finite element model. And here are the second strain mode set, computed from ground vibration testing, using strain response to impulse and spectral POD algorithm. For more details, see the full paper. Here, shown the noise covariance values found with the designated testing I mentioned on slide number 8. Note the values of modes 4 and 5 at the process noise covariance. They are significantly higher than the others, meaning the Kalman state estimator will rely less on them in the prediction. Similarly, the Kalman state estimator will rely in a reduced manner on sensor number 3 at the main spar in the corrector phase. The location of the sensing points used as input are marked in red on the drawing on the right. Sensing points number 2, marked in orange, are the validation points on the next few slides. Here are strain recovery at sensing points 1 and 2 on the spars, using strain mode sets from finite element model. In this case, the response reached to values of about 500 microstrain. We can note that the Kalman state estimator, the yellow line, is with the best agreement with the measurements, the purple line. Although the initial prediction, presented as the model, the red line, is quite off, the Kalman state estimator uses information from the measurements to correct the results. On these slides are displacements reconstruction on the wingtip, an extremely remote location from the Kalman state estimator input sensing points. The Kalman state estimator error is mostly within the motion recovery system error range. The maximal Kalman state estimator error is about 4 mm. Overall, the finite element model strain mode sets deliver quite good shape estimations. What about the ground vibration testing set? The figures on this slide compare the Kalman state estimator strain error while using modes from finite element model or ground vibration testing at all the sensing points. On the left is the mean strain error on the main and rear spars, which is generally within the range of about 15 microstrains, significantly lower than the response itself. On the right is the error covariance. From the low variance values, we learned that the Kalman state estimator errors are small throughout the measurement time. For more results of the nominal case, see the full paper. Moving on to the impact of error-elastic models' airspeed uncertainty. As I mentioned before, the error-elastic plant model is computed for specific airspeed. However, the shape sensing is required also during airspeed changes. To study the effect of uncertainties in the error-elastic model due to differences between the airspeed at which it was created and the test actual speed, we run the Kalman state estimator with models at varying by plus minus 3 meters per second from the nominal speed of 24 meters per second. The tables show the errors in prediction, the strains at the unmeasured locations. These errors are small, in the order of 0.1 microstrains, indicating that an error-elastic model with 12.5% offset from the flight speed yields good prediction. To conclude, the study shows strain to displacement method based on the Kalman state estimator, weights together strain data from fiber optic sensors and error-elastic plant state space model. The method demonstrated on wind tunnel model provides accurate estimations of wingtip displacements and strains at unmeasured locations. Set of strain modes from different sources can be used, such as finite element model and ground vibration testing. And the method has little sensitivity to erratic plant model uncertainties due to airspeeds. That's all. Please see the full paper for more details. I hope you enjoyed my presentations. Thank you for listening.